Alright, now we're going to talk about hyperbolic functions. There's a lot of formulas in here, so you can probably just take pictures of some of these formulas when we get to them, but formulas and equations. Now hyperbolic functions are a class of functions. They're similar to trig functions, and the name is derived by comparing the area of a semicircular region with the area of a parabola. One of the things that you might want to do, let's say we want to find the area of a semicircular region. Well, in order to evaluate this integral, and you don't have to worry about where I got this answer, but in order to evaluate this integral, we would have to involve an inverse trig function, and then when we evaluated this function from -1 to 1, we would get pi over 2, which of course is the area of a semicircle that has radius 1. But if we wanted to find the area bounded by a hyperbolic function, this dark blue area down here, then we would actually have to integrate a function that looks like this from -1 to 1, and what we would get is we would get an inverse hyperbolic sine function in the equation, and so in the function, and so we need to know about these inverse hyperbolic sines to evaluate areas of this nature. Now the 6 hyperbolic functions can be represented using the natural exponential functions e to the x and e to the minus x. So for instance, you can just take this and run with it here, that the hyperbolic sine function, and that's actually the way you read that. Some people will call it sinh, but the hyperbolic sine function, or sinh x, is e to the x is equivalent to e to the x minus e to the minus x over 2. So in other words, if you graph this function or you graph this function, they'd be the same. So that's the hyperbolic sine. Now the cosh of x, which would be the hyperbolic cosine function, is e to the x plus e to the minus x over 2. So the only difference is it's minus. Up here it's minus and here it's plus. Now to get hyperbolic tangent, it turns out that hyperbolic tangent is the same as hyperbolic sine over hyperbolic cosine. So if you took this function, let's say, you took the first expression up here, e to the x minus e to the minus x over 2, and divided it by this, e to the x plus e to the minus x over 2, you're going to get e to the x minus e to the minus x over e to the x plus e to the minus x. And that's your hyperbolic tangent representation. Now the hyperbolic cosecant, it's just the reciprocal of the hyperbolic sine. So you just flip this over and get 2 over e to the x minus e to the minus x, as long as x is not equal to 0. Now the hyperbolic secant is the reciprocal of hyperbolic cosine, so that would be 1 over hyperbolic cosine of x, which would just be 2 over e to the x plus e to the minus x. And of course the hyperbolic cotangent, which is what that should say there, that should say COTH there, not tangent. So the hyperbolic cotangent of x would be 1 over the hyperbolic tangent, so you would just take the reciprocal of what we got over here to get the hyperbolic cotangent. So basically, if you took e to the x over 2 and minus e to the minus x over 2 and added them together, that would be these two dash graphs. That would give you the hyperbolic sine function. So that's where the hyperbolic sine function comes from. And so its domain is all real numbers and its range is all real numbers. Now if you took e to the x over 2 and e to the minus x over 2 and added those two together, that would be these two. When you add these two together, you would actually get this hyperbolic cosine function. And then, I'll just show you the rest of them. And by the way, this one has domain all real numbers, range 1 to infinity. the hyperbolic tangent function looks like this, and it has horizontal asymptotes at -1 and 1, and the domain is all real numbers. The hyperbolic secant, both axes are actually asymptotes, and so the domain would be -infinity to 0 union 0 to infinity, and the range would be -infinity to 0 union 0 to infinity. And the hyperbolic secant, the x-axis is a horizontal asymptote, and so the domain is all real numbers, but the range is just from 0 to 1. So just goes from 0 up to 1. And then the hyperbolic cotangent, y equal plus or minus 1 are horizontal asymptotes here, and so the domain would be all real numbers, but the range is actually, let's see, actually I've got this wrong. The range is everything outside of -1 to 1. Because actually you can see there's not even a graph between y equal -1 and 1, so it's everything from -infinity to -1, and then from +1 up to infinity. So that would be the range of those functions. Now you can freeze the video here or just take a snapshot, but these are hyperbolic identities, and you can easily show these using the definition. Let me just show you maybe one of these. Let's look at the first one. The first one says hyperbolic cosine squared minus hyperbolic sine squared equals 1. Well, hyperbolic cosine squared would be this expression. Hyperbolic sine squared would be this expression. Well, if you squared this and squared this, you'd actually be squaring binomials in the numerator. So if you squared that, you would get e to the 2x, 2e to the x times e to the minus x plus e to the negative 2x. And here you would get e to the 2x minus 2e to the x, e to the negative x plus e to the negative 2x. And so basically when you put those together, everything's basically going to cancel except for this term and this term. But this term, e to the x times e to the negative x, that's just 1. So this is just going to be 2 plus 2, which is 4. So you're going to get 4 over 4, which is 1. And here's another one you can easily show. If you work from the right-hand side, you can say 2 times hyperbolic sine times hyperbolic cosine. And if you multiply those together, you're going to get 2 over 4. And then these are difference of squares, so you're going to get e to the 2x minus e to the minus 2x. And then when you divide 2 into 4, you get 2. Well, since these are 2x's, this would be what you would get if you took the hyperbolic sine of 2x rather than the hyperbolic sine of x. So anyway, you can prove those if you need to. Using those formulas involving e to the x and e to the minus x. Okay, now again, you can take a snapshot of these pictures or a screenshot, and on the left side I've given you the derivatives of the 6 hyperbolic functions, and on the right side I've given you the integrals that involve these hyperbolic functions. So you can see that basically, since we know the derivative of tangent, hyperbolic tangent u is hyperbolic secant squared u prime, then we know if we integrate hyperbolic secant squared u du, we'll get hyperbolic tangent, of course, plus a constant. So you could prove these using their exponential form, because, and I'm just going to go ahead and tell you, if you take the derivative of this, which is hyperbolic sine, you're going to get 1/2 times, you're basically going to get 1/2 e minus e to the minus x times minus 1, and that's going to be 1/2 e to the x plus e to the minus x, which is actually the same as hyperbolic cosine x. And so the chain rule would actually follow for the hyperbolic sine of u. And if you wanted to do the hyperbolic tangent of u, well, since you know that's equal to the hyperbolic sine over the hyperbolic cosine, you could actually use the quotient rule there, and you would find out that if you take the derivative of hyperbolic tangent, you're actually going to get 1 over hyperbolic cosine squared x, which is same as hyperbolic secant squared x, and then you can extend it to the chain rule for hyperbolic tangent of u. So if you wanted the derivative of hyperbolic sine of x cubed minus 1, well, remember that's the hyperbolic cosine of x cubed minus 1 times the derivative of x cubed minus 1. So you just get 3x squared times the hyperbolic cosine of x cubed minus 1. If you want the derivative of natural log of the hyperbolic tangent of x, well, since this is natural log of something, the derivative of natural log of u is 1 over u, so that'd be 1 over the hyperbolic tangent, and then you would have to multiply by the derivative of hyperbolic tangent, which would be hyperbolic secant squared x, and then you can do a little bit of dancing with some of the identities, and you can actually write this as 1 over hyperbolic sine x, hyperbolic cosine x, which is the same as hyperbolic cosecant x times hyperbolic secant x. And then here's one where you actually are going to find, let's see here. Okay, that x squared wasn't supposed to be there. So if you take the derivative of hyperbolic cosecant x, it's minus, there's a minus, hyperbolic cosecant x times hyperbolic cotangent x, and then of course the derivative of e to the 5x is just 5e to the 5x. So that would be the derivative of that function. Let's find the extrema of this function. Okay, so this function, you would have to, the first term you'd have to use the product rule. So the product rule, I'd take x minus 1 times the derivative of hyperbolic cosine, which is hyperbolic sine x, and then I take hyperbolic cosine x times the derivative of x minus 1, which is 1, and then I have minus the hyperbolic cosine of x, because that's the derivative of hyperbolic sine x. Well, the hyperbolic cosines will cancel out, and so I'll just get x minus 1 times the hyperbolic sine x. Well, if x minus 1 is 0, then that means x equals 1, so that would be a critical number, and the hyperbolic sine x would equal 0 only if x is 0. And so the critical numbers are 0 or 1. And so now, if I took the second derivative of this, the second derivative would actually equal this. X minus 1 hyperbolic cosine x plus hyperbolic sine x. So you can check that yourself. Now, if I evaluate the second derivative at 0, I'm going to get negative 1, which is negative. So f of 0 is a relative max. And if I evaluate the second derivative at 1, I'm going to get a number greater than 0. So f of 1 is a relative min. And so if you graph this function, you can see here that we get a relative max here at 0, negative 1, and then you get a relative min at x equal 1, and actually that's 1 and negative 1.175. And of course you get the y values by plugging them back into the function up here. Down here it shows you how you actually can get the y values, because I went back to the exponential form to figure it out. So you can put the hyperbolic, you can put these hyperbolics back in exponential form and then let x be 0, and then you can put them in, do the same thing, letting x equal 1. So that's what you're going to have there. And let's see what else there. So that gave me the relative max. That gave me the y value for 0 was negative 1, and the y value for 1 was this number, e to the negative 1 minus e over 2. So anyway, that's how I got the y values. Okay, I'll probably finish this up with an application, and then I'll talk about a couple of other things. I'll let you just copy this application, take a picture of it, but notice I changed this function that we did before. I changed it into a hyperbolic cosine function, and then when I took the derivative of that, I was able to show that at x equals 0 it yields a minimum.